Remember the definition of AI? It's the study of agents that can perceive their environment and act rationally. Russell and Norvig's standard model of AI focuses exactly on that, rational behavior. But that's not the whole story. Even if an AI acts rationally, if its behavior doesn't align with human values, we could be in trouble. That's why we also have to deal with something called the value alignment problem.
Like, comment, subscribe, and turn on notifications.
Today's topic is AI, machine learning, deep learning, and reinforcement learning. Many people think they're all the same thing. Some even think machine learning is AI. But nope. Machine learning is just one part of AI. Deep learning and reinforcement learning are even more specific subfields of machine learning. And where they overlapped, that's deep reinforcement learning. Yep, like what AlphaGo used. Let's see how these concepts relate with an example. First, the biggest circle, AI. About 15 years ago, I bought a robot vacuum cleaner. Now, the one in this video, it's wow, slam it into walls like it's training for a demolition derby. Mine wasn't that intense. Anyway, its movement was simple. It moved forward, turned, moved again, turned again. If it hit something, it turned. Sometimes left, sometimes right. Most likely, the rule, turn in a random direction when hitting an obstacle, was hard-coded inside its brain. No running, just fixed instructions. In AI terms, when it hit an obstacle, that was a percept, information it got from the environment. Changing direction was an action. AI is all about agents taking rational actions based on percepts. Now, sure, my vacuum's behavior wasn't really rational and it didn't learn anything. But hey, it still sensed the environment and reacted according to predefined rules. So technically, it meets the most basic definition of AI. Now, let's move to machine learning, a core subfield of AI and the driving force behind modern AI. A few years later, I got a newer model. This one didn't just bump into walls. It used ultrasonic sensors to avoid them before impact. Why? Because it could make decisions based on past experience. It had learned that objects of a certain height and texture can be crossed and others should be avoided. Here's how it learned. First, it deliberately ran into different objects to collect data. It measured height and softness with its sensors and recorded whether it succeeded or failed to cross them. Now, let's plot the data. The x-axis is texture, y-axis is height. Green dots mean success, red dots mean failure. See? All the red dots are above this line, all the green dots are below it. That means our robot learned a simple boundary between success and failure for 5 objects. But then, here comes a 6th obstacle. It did cross it, but the yellow prediction line said it couldn't. So, we adjust the line, move it, tilt it, until it separates successes and failures correctly. This line is called a decision boundary. Finding the best decision boundary, that's called learning. Yes, there's math behind it. We'll dive into that when we get to perceptrons. Once the robot learned this, it could decide just from height whether to cross or avoid an obstacle. And this type of algorithm, which separates data with a straight line, is known as traditional machine learning, or shallow learning. Now, let's talk about deep learning, the rock star of machine learning. To see how it's different from traditional ML, let's check out the latest robot vacuum. This one's got a camera. For a human, that's basically an eye. So imagine it's cleaning and it sees a cat. Old robots, they'd either bump into it and turn, or sense something's there and avoid it. This one, it actually recognizes, oh, that's a cat, just like you and I do. Once it knows it's a cat, it could make a sound to scare it off, or just wait politely. But here's the catch. You can't figure out cat just from height or texture. You need RGB values, shapes, patterns, tons of high-dimensional complex information. And it still needs to tell different cats apart like in these pictures. the technology that can learn and classify this kind of complex, high-dimensional information. That's deep learning. For image recognition, the superstar deep learning model is the CNN, Convolutional Neural Network. Here's how it works. Convolutions scan the image, detecting low-level features like edges, lines, and curves. Then it combines those into higher-level features, ears, eyes, tails. You get the idea. After multiple convolution layers, the network passes these features into a fully connected layer to decide cat or not a cat. In modern CNNs, that final step often uses global average pooling instead of a traditional fully connected layer. So now the picture's clearer. Machine learning means algorithms that learn patterns or rules from given data so they can predict or classify new data. It includes both linear models and nonlinear, complex neural networks. And those deep, multi-layered networks are what we call deep learning. If it's not deep learning, we often call it shallow learning. Shallow typically means there's no deep, multi-layered neural network, usually one hidden layer or none. Shallow models are simpler and more transparent. With math tools like linear algebra, calculus, and probability theory, we can fully understand how they work and why they give a certain result. That's why studying shallow learning means doing a lot of math. And trust me, that math intuition will help you a lot in understanding deep learning later. In fact, when I first studied deep learning, I thought it was easier because it's basically shallow learning principles, just extended. And ironically, on paper, you see less math when learning DL models, though under the hood, it's still very math-heavy. Why? For example, if you already know derivatives, backpropagation, and optimization, then when learning CNNs, the only new math you'll meet is convolution. Deep learning can, in theory, be explained mathematically, but it's so high-dimensional and complex that we often can't pinpoint exactly why a model made a certain decision. If you ask it, "How exactly did you tell this was a cat?" it can't really explain. Many, sometimes thousands, of filters fire, some feature vector gets activated, but it's beyond human-level interpretability. So in practice, we rely on intuition about what's happening inside, rather than fully decoding every step. Good news? Bad news? I'll let you decide. Now, reinforcement learning, or L, is all about choosing the best action in the current situation to reach a goal. Imagine this grid is my living room. Some cells have obstacles. Stepping on them gives a penalty of -20. Every move costs -1. Reach the goal plus 100 reward. As value iteration runs, the value of the goal spreads backward through the grid, updating the policy. So if my robot starts here, the best move is right. From the next cell, best move, right again. Then at the far right corner, go up and boom, you reach the goal. This example's so simple, it's obvious the policy will converge to that yellow arrow path. But let's make it trickier. Now, there's a dusty area that needs to be cleaned as quickly as possible. We assign it a +10 reward. In RL, the value of each cell based on rewards spreads through the environment over time. The agent chooses actions that maximize this value, and as it repeats the process, the policy converges. So eventually, the robot learns to pass through the high-reward dusty area on the way to the goal. Finally, the intersection of the two. Deep reinforcement learning. This is one of the core technologies behind AlphaGo. It combines CNNs and RL. I'll skip supervised learning in Monte Carlo tree search for now. AlphaGo uses a CNN to see the Go board, basically treating it like an image, and understand its state. Then, it predicts which moves are good. Because rewards from winning propagate backward to the moves, the system knows which actions are best from the current state. If we compare this to our robot vacuum, The Go board state is the robot's cell position. Moving Go is the robot choosing where to go next. AlphaGo understood the board state through CNNs, acted based on a learned RL policy, and that's how it defeated Lisa Dahl.